Hello, let's do this question, which I did a couple of days ago. It was a math question, plus, and you'll see it's binary search as well. But let's read the question. So, an ugly number is a positive integer that is divisible by a, b, or c. Right. So any of these numbers, and it would be an ugly number. Given four integers, n, a, b, c, return the nth ugly number. Right, so let's go through this example. So starting from, I think, so is 0, do we count 0 actually? Yes, I don't think, no, 0 is not divisible by anything, I don't think. I don't think we count 0, so that means the ugly numbers go for our 2, 3, 4, 5, 6, 8, 9, 10, and the numbers are 1, 2, 3, 4, 5, 6, 7, 8. So the fourth ugly number, the third one that they want here would be correspond to this one here, so we return 4. Okay, so why don't we just go through all possible answers in a linear loop and just figure out if it's a ugly number. And you can do that if you just take the number modulus each of these and see if any of them are equal to 0. If the modulus equals to 0, then it's an ugly number. Okay, that would work, but what's the maximum that we could go up to in this linear loop? So it's guaranteed that the answer will be in the range from 1 to 10, 2 times 10 to the power of 9, right? And since we can only do up to like 10 to the power of 8 operations per second, and assuming that time limit is 1 second or something like that, then this would take too long. So we can't just do a linear loop. We would have to do, you need a little bit of help. I need a little bit of help to find what to do, but you can do a binary search. So binary search relies on a function, let's call it f, that if we pass in the number, so if these are your x's, you pass in the number there, this will return number of ugly numbers less than or equal to x. Right, it doesn't matter if x is an ugly number or not. You can still return the number of ugly numbers less than or equal to x. So how do you do that? Okay, well, let's take this example, 2, 3, 5. So I guess what we can do is say, for example, I know that the index of 10 is 8. So let's hopefully I can find what f of 10, I can get 8 out of f of 10 using some formula. So let's try to f of 10 is equal to, okay, so maybe we can do something like, if 10 is divisible, how many times 2 goes into 10? So that'll be 10 divided by 2, and it goes into 5 times. And we could do 10 divided by 3, and 3 goes into 10 3 times, plus how many times 5 goes into 10? 2 times. Now that's equal to 10, which is wrong. Why is it wrong? So let's see. So we counted 2 for the 2's. We counted 2, 4, 6, 8, and 10. So that's where all the 5 numbers come from. And then for the 3 here, we are counting 3, 6, 9. That's where all the 3 numbers come from. And immediately we see we're actually repeating one of those numbers. So that's the reason why we're overcounting and getting a different, bigger answer. And let's just finish it off. So we have also 5 and 10. And we see that we're also repeating the 10, which means, so we're repeating 6 and 10, so that means we're 2 more than what we want. Okay. So how do we get rid of this problem? Well, we know that, okay, maybe it'll be tempting to think that, well, 6 is equal to 2 times 3, which is equal to 3 times 2. And we also know that 10 is equal to 2 times 5, which is equal to 5 times 2. Maybe that's the reason why they're repeated, right? That's a good reason why they're repeated. So what if we just subtract from the sum, since so this is add all of these ones and subtract all multiples of 6 to prevent double counting. 6, and there's only one 6, and there's only one 10. So I can subtract those two. Would that work and get me 8? It works for this case, right? But what if we consider the next example? Okay. In the next example, we see we have a 2 and a 4, but a 4 is divisible by 2. So that is not a case we've considered in the first one. In the first one, A, B, and C are all prime numbers. Here, it's not. The first 2 are prime numbers, but the second one is not a prime number, but also it's divisible by 2. So let's see what we get if we try to do our initial method. So we get f of, okay, let's see, let's put this stuff here. Okay, so you have 1, 2, 3, 4, 5, 6, 7, 8, 9. This would be 8. Okay, let's try to find what the answer for 12 is. So 12, so f of 12 is equal to, it will be equal to 12 divided by 2, which is 6, plus 12 divided by 3, which is 4, plus 12 divided by 4, which is 3, which is equal to 7 plus 6, 13. Now this is definitely bigger than 8. So what, but okay, let's also subtract the multiples of A times B, multiples of B times C, and also the multiples of A times C. So let's subtract multiples of 6, so there'll be 2. Let's subtract multiples of 12, that's 1. And it's also subtract multiples of 4 times 2, which is 8. And there's also one of those. So in the end, we get, so initially this was 13, and this is 4, so we get 9. But the answer is 8. So what happened there? Well, let's consider what everything is. So for 2, 3, 4, we have the multiples of 2, 2, 4, 6, 8, 10, and 12. We have the multiples of 3 as what? As 3, 6, 9, and 12. We also have multiples of 4 as 4, 8, and 12. Okay. So we see that for all fours are contained within multiples. All multiples of 4 are contained within multiples of 2. That's the main point. And we've actually, the reason why we have one more is because we haven't subtracted the double counting of 4. But we did, to an extent, try and do to delete these ones here, but we missed one. But why did we miss one? Okay, so let's see. So we wanted to add these, and we want to subtract multiples of. So let's see. We have 6 multiples of 6. We get 6, 12 multiples of 3 times 4 is 12, so that's one of those. And we have multiples of 2 and 4, which is 8. So there's one of those as well. That's why we have a 2, minus 2, minus 1, minus 1. If we were to subtract multiples of 4 instead, we would get 4, 8, and 12. But then we're subtracting too much. We're subtracting too much because we actually have to add on back the overlap between all 3 that we subtract. This is the inclusion-exclusion principle. So the overlap between all 3, we have potentially subtracted 12 too many times. So we have to add back the overlap between all of these. And the overlap between all of these would be the least common multiple between all these numbers, which is 12. If you multiply all these together, 4 times 3, which is already 12, times 2 is 24. We can subtract 24, but that's not the least common multiple. The least common multiple is 12. So we have to add back on 1. So if we would somehow get all of these, we would get... okay, let me get back to that point later. Okay, so let's first of all focus on how we actually get to the point where we actually subtract multiples of 4 and not just multiples of 8, where we got from in our initial method of just multiplying 2 and 4. If we get the least common multiple between 2 and 4, we get 4, and then we can subtract all multiples of 4 to subtract all of these. Okay, but we see, and what is the least common multiple? It's the multiple that is the least. So if 2 and 4, for example, the least common multiple is 4, because I can multiply the 2 by a 2 and the 4 by a 1. So let's say, for example, I have a function called LCD. Then that means by the inclusion-exclusion principle. So let's take a look at what that means. And it's best visualized using a Venn diagram. I don't know, something like this. So imagine, that was my answer before, but the point is, imagine we are subtracting all multiples. Imagine the circle means we are subtracting all multiples of a single number, A, B, and C. So that's what all these represents. All multiples of 2, for example, all multiples of 3, all multiples of what was it, 4? Now all multiples of 2 and 4 definitely overlap, and that's represented by this bit here. There may be no overlap between 2, but there is a case in here where actually all 3 would overlap. And that number in the middle, you can imagine, would be just a 12. So it'll be a 12 in the middle here. And we've subtracted that 3 times if we subtract the overlaps, right? So we have to add that back one more time. Because if we just count all the circles, then we've counted the middle part 3 times, and then subtracting all the overlaps subtracts it 3 times, so then you get nothing. So add it back one more time, and it's there. Yeah. So let's think what the formula is now. So the formula would be the LCD. So we want to get the f of x is equal to the LCD is equal to x divided by LCD of A plus x divided by LCD of B plus the x divided by LCD of C. Then we subtract the overlaps. So these represent each individual circle that we saw in the Venn diagram. Then we subtract the overlaps by doing. Sorry, this doesn't make sense. This is you can't get the LCD of a single number. Then we subtract the overlaps by doing x divided by LCD of A and B minus LCD minus the LCD of B and C minus x divided by LCD of A and C yes, and then we add back on the middle part, which is the LCD x divided by LCD of A and B of A and the LCD of A and B. So it's the LCD of all of them is equivalent to this. Oh, wait, hold on. Hey, this is C. So that's the formula. You see these part represent the overlap, these 3 overlaps, and this one here represents the middle, the very middle, the one that gets overlapped 3 times. So add that back on. Alright, so that's the function. We figure that out, but how does the binary search work? So this would return the index, right? So if this returns an index less than our target number n, our target index n, then we know to search within the whole range of answers. So the whole range of answers is this. Let's try the middle one, for example, and let's say that's less than the answer. Then we know that we can reduce our range of search between, okay, so halfway would be 10 to the power of 9. And also 2 times 10 to the power of 9. If f of x of the middle value of this is less than was less than our target n, then we could search within this range instead. In fact, we don't need to check this again, this value, because we know that's not the answer. Okay, but there's a problem still. Yeah, there's a lot to this question. There is the case where in between 2 ugly numbers, a number that we find in the range has the same number of ugly numbers less than it, because that's what the function finds. So which one out of a range, a certain range within the answer range that have the same number returned by f of x is actually an ugly number? Well, it turns out within only one of them within that range is an ugly number, and it's the very first one. So say, for example, if we do this, if we get this range here, we know that the number of ugly numbers returned, so if f of x is here, f of x returned for this value is 1, 2, oh, this will be 1 because it's including itself. This will be 2, 3, 4, 5. So that's just the index. 7, 8. Now in between, say, 6 and 8, there is a 7 here somewhere. That's not an ugly number. But that value would also return a 6. So, and say, for example, we land on 7, on 8. No, sorry, this will return a 5. Let's say, for example, we land on 7. We don't want to return 7 as the answer. In case n, so let's say, for example, n is equal to 5. If you land on 7, we're like, oh, okay, so let's return 7. But we don't want to return 7 because it's not an ugly number. So it turns out that the ugly number is the first one within these duplicates, which is 6. And that makes sense because when suddenly the number of ugly numbers less than the current goes from 4 to 5, so it jumps by 1, then we know the first one there is ugly number. And then if it repeats, then we know that this one's not an ugly number, because if it was, then this would have increased. The index would have increased. So we also need to take that into account and return these values, the first one and within the range, using the binary search. Okay, let's figure out how to do that. First of all, let's copy this. And here, and write this function. Okay, so let's see if we actually need to use ints, or should we use a bigger data type. So the range goes up to 2 times 10 to the power of 9, which is very large. A long would be more appropriate, so let's actually look. Max size of int. Right, so that's that's 2 billion. That's 2 times 10 to the power of 9. And that's what they said here. So this is actually less than, this would fit in an int, but there is a problem depending on the implementation of LCD. So how does LCD look? First of all, let's just we should probably write the function LCD first. Let's say it returns an int for now. And the formula for LCD is the numbers that it takes in A times B. You multiply them together and you divide by the GCD of A and B. Why is that case? So GCD means the greatest common divisor, and that's actually built into C++. The greatest common divisor of two numbers is the greatest factor that can go into both. If we subtract the GCD from both of these numbers, not subtract, but divide the GCD from both of these numbers, and then multiply them together. If we subtract the GCD of both of these numbers from here and here, then that means these two are definitely not related to each other. They have a different set of prime numbers. That means if you multiply them together, you'll get the least common multiple. Yes. Okay, but there is a problem. So we're multiplying A and B. Well, A and B could go up to 10 to the power of 9. So we're potentially multiplying 10 to the power of 9 times 10 to the power of 9. So that would overflow in int. So we should use a long. So we could type def a long to be an LL, and pass in that as well, like this. So max size of that's 6, 9, 12, 15. Yeah, so 18. Yep, that's like double the size basically, and that makes sense. Not double the size, in fact. It's not double the size of an int. It's actually the power is doubled. So, and that would make sense because if I multiply two of these together, I get 10 to the power of 18, and that just fits in a long. So that would work. Okay, so that means we can know how to implement f of x. So let's make that return something like this. All right, return that. But also has to take in a, b, and c. Let's also see if it makes it more efficient if we just take in a reference to these instead. It shouldn't make much difference though. Okay, and then here we do the binary search that we talked about. So the binary search that we're going to do is the easiest way I found. There's multiple ways to do it, but if you say LL is a low, so this is the start of our range, and we also need a high, and we basically modify this range until they're next to each other, and then one of these would be the answer, because low and high actually search within the answer range directly. So one of low and high would be the answer. Now, should I make it so that low is less than or equal to the answer, or strictly less than the answer, and make high greater than or equal to the answer? So that's a good question, and that depends on what we're trying to do here. So if we eventually will find that our low, if we're searching for 5 in this case, if we're searching for 5, we'll get down to, we could either get have low here and low high here. So this will zoom in on the range where we have low is equal to this 5 here and high is equal to this 6 here. That's if this will happen. We'll find that low is equal to the wrong answer here if we make it so that the invariant is that low is less than or equal to the answer, and high is definitely greater than the answer. If we make it so that, will that work if so let me write that down. Say low is less than or equal to answer, and high is greater than answer. If we consider this is the only position that low and high will end up. And we'll return low because it could be potentially equal to the answer, but it's the wrong answer. So let's try and move this here. With these invariants, this doesn't fit with this, because because low in this case is, yes, let's less than or equal to the answer, but high is not strictly greater than answer. Actually, high is also equal to answer. So this doesn't work with these invariants. So if you just change it so that if low is less than the answer and high is greater than or equal to the answer, then this would work, and the other way doesn't work. So it's all about the invariants when you start off the binary search. So this is the invariant we want. Let's copy that and put it here. Okay, we'll delete it later, but so if low is less than answer, then the range is this, right? So that means low will be definitely less than the answer if low is equal to 0, because the lowest lowest number in the range is 1. So make this 0, and so this is less than the answer, and make this equal to greater than or equal to the answer. This is, yeah, it should be this, but if that's greater than or equal to the answer, then I could just use the last number in the range. So that's 2e9. That's yeah, greater than or equal to the answer. All right. And now we can do a binary search. So if while low is less than high minus 1, so as soon as low and high are next to each other, it would break out of this loop. Because this is saying if low is equal to high minus 1, then that means they're next to each other, so we break. And they can never equal each other. They can never equal each other because, the invariants don't allow it. And the invariants we enforce in the actual implementation. So in binary search we would find the mid, which was equal to low plus high divided by 2. Make sure we use LLs. And we say if the f of the mid value is, let's say, for example, less than the answer, then we know we want to make low equal to mid, because that fits this invariant here. Mid is something that low could be because mid is less than the answer, and that fits this one here. Otherwise, else high is equal to mid. Otherwise, high would fit it perfectly as well. This invariant here. And at the end, we just return answer. So let's see if I made a mistake here. Or not. So this is this should be BC here. So it's AB, BC, AC. Yeah, that looks good. Run that. Compilation error. Okay, so non-const L value reference to. Oh, okay. So the problem is here. This is returning a non-const. So to make this work, this is a bit overkill, but I have to make these a const whenever I can. In fact, it's I like doing west const. No, this is east const. Sorry, yeah, I like doing east const. because this is returning some number that's a temporary value. It's an R value. It's not, doesn't have a actual location on the stack. Well, it actually does, but it's not bounded to a handle. It's just a free value, is kind of like what a R value is. So there's no real reference to an R value because it doesn't have a handle. But I can bind it to a const reference. Invalid. Oh, yep, I did mean that. If mid. Oh, yes, forgot to pass in the A, B, and C. And this should not be answer, this should be N. And this should be hi. Whoops. Okay, so that works. This is a big one. Let's try these answers here. That's 2. Okay, so let's give that a go. Perfect. And that's that.